All right, well, we're going to pick back up with phase changes that we had talked about before. And then we're going to move into calculating the amount of heat it takes to go through like several phase changes. If we want to take ice to steam or whatever, we're going to actually calculate how much heat has to be put into that. So let's get started. All right, so with phase changes that we talked about before, you can either have things like a solid going to liquid, which is melting, also known as fusion, or going back from the liquid to the solid, freezing, or condensation, vaporization. So we talked all about the different phase changes. Well, every time there's a phase change, there's a change in energy of the system. So in order for a substance to change to a less ordered state, there must be energy supplied to it to make it go to a less ordered, because that's against nature. And that energy has to overcome the intermolecular attractions. The stronger the intermolecular attractions, the more energy it takes. Okay, so energy is supplied, we talked about that before, to break apart, for instance, with water, the hydrogen bonded molecules in the solid to let them become a liquid, and then just some of the hydrogen bonds are broken. Then for the liquid water to become a gas, all of the hydrogen bonds have to be broken. So that takes energy. So for water, the heat of fusion, the amount it takes to melt water is 80 calories per gram. Okay, so the amount it takes to heat 1 gram of water to make it melt is 80 calories. Or if it was in kilojoules, it's 6.02 kilojoules per mole of water. That's for melting 1 gram of ice. Okay, if we're going to vaporize 1 gram of liquid water, it takes 540 calories to take liquid water to gaseous water. Okay, and if we were going to do it in kilojoules per mole, it's 40.7 kilojoules per mole. So you can see there's a lot more heat needed to vaporize 1 gram of water versus melting 1 gram of ice. Why? Why is the heat of vaporization so much larger? It's because, again, to vaporize water, all the intermolecular attractions have to be broken. And in water, those are hydrogen bonds. Whereas to melt it, only some of the intermolecular attractions are broken apart. Okay, that's why it takes much more energy to vaporize versus just melt. So we had seen a diagram like this before. When you're melting versus freezing, freezing would be you are removing that much heat, okay, removing to freeze, versus melting, you're adding. Okay, and then the same thing with evaporating or vaporizing, you're adding to evaporate, whereas when you're going back the other way, condensing, you're removing that much heat. Okay, so again, the heat of fusion, how much heat it takes to melt it. The heat of vaporization, how much heat it takes to vaporize it. So if we were going to calculate how much heat must be removed to freeze 500 grams of water, we would just multiply the amount of water times the heat of fusion, which tells us it's 80 calories per 1 gram. Okay, so that would end up to be 40,000 little calories, which is 40 kilocalories. Example 2, how much heat must be added to vaporize 500 grams of water? Well, in that case, the heat of vaporization is 540 calories per 1 gram. So we would multiply 500 times 540, and we would get 270,000 calories to vaporize 500 grams of water. So multiplying the mass times the heat of fusion for figuring out how much heat it would take to melt a certain amount, multiplying the heat of vaporization times the mass to figure out how much it takes to vaporize a certain amount of water, in this case 500 grams. Well, we're going to apply that to some curves, warming curve, also known as heating curve, versus a cooling curve. So we talked about this before, that when you have a solid, it will start at a certain temperature, and then you're going to heat until it reaches the melting point. At the melting point, it will, it's not liking me writing on this, I guess. At the melting point, it will not rise in temperature anymore the whole time it's melting. That is because all that heat is going into break apart the sum of the intermolecular attractions. Okay, and then when it's all liquid, after it's all melted, then the heat can rise again until you reach the boiling point. And then at the boiling point, again, there is just this flat line. What happened here? No, it cloned it. Until you can reach the, until all of it is vaporized. I have a clone here. And then once it's all vaporized, the temperature will rise again. So every time it's going through a phase change, there's no change in temperature. When there's a change in temperature, it's all in one phase. So from solid to liquid, it's a flat line. You can see no raise in temperature. Then once all of it's a liquid, the temperature rises again until it's becoming gas. Then the whole time that it's vaporizing, the temperature doesn't rise until it is all a gas, and then the temperature can rise again. So these different steps all take energy. And if we were going to take a solid all the way up to a gas, there's actually 5 separate steps. If we were only going to take a solid to a liquid, that would only be, if you're going to change the temperature of the liquid, it would be 3 steps. If you're only keeping it at the same temperature and just melting, that's just 1 step. But if it's a solid that you have to heat up to its melting point and then melt it and then have it heat up, that could be 3 steps. Okay, and whenever there's a temperature change, it's the specific heat equation that we had before, which is the Q equals mass times specific heat times change in temperature. That's always when there's a change in temperature. When there's no change in temperature, then it's just the heat of fusion for melting or the heat of vaporization for vaporizing times the moles. So we're going to do a problem like this where we have multiple steps. Okay, so again, it's a step-by-step process, and we can calculate how much heat it takes to change a substance in one phase at one temperature to a different phase at a different temperature. And the Q equation that we just used with specific heat is going to be used anytime there's a temperature change. And then during the phase change, we'll have to know the heat of fusion or the heat of vaporization, and we have to know the amount of the substance. That has to be in moles. So we are going to do a problem like that. So calculate the amount of heat that must be added to change 50 grams of ice at minus 15 to liquid water at 65 degrees. So this, I always like to draw my different steps, and that kind of guides my problem. So I know I'm going to take ice at minus 15, and then I'm going to heat the liquid water up to 65. So this isn't exactly to scale. Okay, but I would start here, and it's going to rise in temperature until it hits 0 degrees, because this is liquid water. This is ice, solid water. And so at 0 degrees, that's where the melting happens. And then once all of it's melted, it can continue to rise to 65. So this problem has 3 steps. So step 1, I'm going to take ice at minus 15 degrees to ice at 0 degrees. So really important, you cannot do a phase change and a temperature change at the same time. Only a temperature change is going to be in the same phase. And then a phase change, the temperature's not changing. Okay, so ice at minus 15 to ice at 0. Since the temperature's changing, that's my Q equation. Q equals mass times specific heat times change in temperature. So plugging that data in, I have 50 grams of ice. The specific heat of water is 4.184 joules per gram degrees Celsius. And my change in temperature is always final minus initial for change. And that is, it's going to have to stop at 0 degrees. And it was negative 15 degrees. So my temperature change is 0 minus negative 15, which is positive 15 degrees. So when I multiply that out, 50 times 4.184 times 15, I get 3,138, and that will be joules, okay, because my specific heat was in joules. Your specific heat has to match your Q. The grams cancel and the degrees Celsius cancel. So for that first step, I'm putting in that many joules to get my ice to heat up from minus 15 to 0. Okay, and so I would be right here. Now I'm going to melt it. So to melt it, I'm going to take ice at 0 degrees to liquid at 0 degrees. So I need to know the heat of fusion, and I'm going to multiply that times the moles of ice. So I have a conversion to do here. I need to take the grams of ice, which is 50 grams, and I need to divide it by its molar mass of 18 grams per mole to get moles. So 50 divided by 18 is 2.78 moles. So 2.78 moles, and the heat of fusion is, oops, it's a times 6 kilojoules per mole. So 6 times 2.78 is 1.67 kilojoules, which times 1,000 will put it into joules. Okay. So that was step 2. Step 3 is now up here. I'm already in liquid at 0, and I can take my liquid up to 65. So I'm going to take liquid water at 0 degrees to liquid at 65 degrees. So now it's another change in temperature. So it's Q equals mass times specific heat times change in temperature. So my mass is still 50 grams. The specific heat is 4.184. And my change in temperature is, I'm ending at 65. So that's T final minus T initial, which is 0. Okay. So now I have 50 times 4.184 times 65 equals 1,360. Wait, is that right? I put it wrong. Oh, 13,600 joules. Okay, 13,600 joules. Okay, is my heat. So now I just add those together. So I had, from the first step, I had 3,138 plus, these are all in joules. From the second one, I had 1670. And from the third one, I have 13,600 joules. So adding up my 3 steps, I get 18,408 joules. Okay, and that's how much heat total it takes. You do each step separately, then you add them up together to get your total amount of heat, which rounded to sig figs, I would keep at 18,400 joules total. If I were going to cool something, it will be the same process, but the heat of vaporization is minus the heat of condensation. So I just put a negative value on the heat on the heat of vaporization to make it heat of condensation. And let's see, what am I doing? I'm cooling steam to liquid water, and I don't need the specific heat of ice here. All right, so I'm going to take liquid water that's at 85 degrees. Oh no, I'm going to take steam, sorry, that's at 125 degrees. And I'm going to cool that down to the condensation point, which is 100 degrees. And then I'm going to, once it's all condensed to liquid, I'm going to cool that to 85 degrees. So I have, again, 3 steps. This time I'm removing heat. So this will be a negative value overall as I am taking out heat, but it's the same idea. So step 1 is I am taking steam at 125 degrees. and I'm going to take it down to steam at 100 degrees. So since it's water, I know the boiling point or the condensation point is 100 degrees. If this were a different substance, it would have to tell us what the boiling point or the melting point of that substance is. So in this case, it's water, so I know it boils at 100 degrees, which means it condenses at 100 degrees. So this is a change in temperature. So Q equals mass times specific heat times change in temperature. So I noticed that there is a little mistake in this problem. It gave me the specific heat of ice. I need the specific heat of steam. Okay, but it is also right around 2 joules per gram degree Celsius. So for that, I'm just going to use that. I think it might be 2.1. I'll look that up later. But for now, we're just going to use that. So we have 50 grams again times the specific heat of steam, which is I'm going to use joules per gram degree Celsius. And then the change in temperature, it's going from 125 to 100. So final minus initial is 100 minus 125. So this is where I'm going to get my negative sign. Okay, that's going to be a negative 25 degrees. So negative 25 times 50 times 2 is negative 2,500 joules. That's how much heat has to be removed to cool the steam from 125 down to 100. Okay, step 1. Then step 2, it's going to go through the phase change, which is condensation. So 2, I'm going to take the steam at 100 and I'm going to take it to liquid at 100. Okay, condensation. So the negative, the heat of vaporization, equals the heat of condensation. And so I need negative the heat of vaporization times the moles to get that phase change. So I have 50 grams of water divided by 18 is the molar mass. So 50 divided by 18 is 2.78 moles. So my heat of vaporization is negative 40.7 kilojoules. That should be kilojoules. Oh, 2 mistakes in this. That should be kilojoules. And that is times my 2.78 moles. So that should have said the heat of vaporization is 40.7 kilojoules. So when I multiply those together, 40.7, and that's negative, times 2.78, that will be negative 113 kilojoules, which is 113,000 joules negative. Okay, so that's how much heat it takes to condense that much steam. And now my third step is I'm going to take that liquid at 100 degrees and cool it down to liquid at 85 degrees. 5. Okay, so now that's another Q equals mass times specific heat times change in temperature. So I still have 50 grams. The specific heat of liquid water, 4.184 joules per gram degree Celsius. And my change in temperature is 85 minus 100, which is negative 15. So 50 times 4.184 times negative 15 is negative 3,138 joules. So now I just add those together. So it's negative 3,138 joules plus negative 113,000 joules plus negative 2,500 joules. Okay, and that equals negative 118,600 joules. So that is my total answer when I add the three steps together.